Welcome to Chemical Process Safety. This video is titled Target Concentrations for Inerting. Now, in the next video, we'll talk about some equations that you can use to determine how to inert a vessel. But before we do that, we have to know what concentration we're actually shooting for. That's a key parameter in those equations. So this video will cover that. Now, in addition to regular operation, there are two special situations that require attention. One of them is when you are preparing to take a vessel out of service. So this could be for routine maintenance or for cleaning or whatever. But if you are preparing to take a vessel out of the process for any reason, you're going to open it up. And when you open it up, you are going to potentially mix air with the fuel and potentially have a flammable mixture form. So it's helpful to think about this in the context of a flammability diagram. I've drawn in just an example of what a flammable zone might look like in red lines here. And then I've also drawn in the air line for reference. Remember that this point right here corresponds to air, where I have 0% fuel, 79% nitrogen, 21% oxygen. So what would happen, for example, if the headspace in the vessel were, let's call it 50% fuel and 50% nitrogen? So that would correspond to this point that I'm circling with my mouse right now. You might say, well, that lies outside the flammable zone, and I would agree with you because this point that I have in my mouse now is not inside the red triangle that I've drawn on the inside here. But what is going to happen if I open that vessel up and start mixing it with air? Remember that the ternary diagram, I can simulate a mixing process by drawing the 2 points and then connecting them with the straight line. So think to yourself, what would happen if I have fuel nitrogen mix here and I mix it with air? What is going to happen? And I've just drawn that in with the green line so that we can better visualize. But look at what happens. If I have the right mixture, it is going to go through the flammable zone. So again, although this point was not flammable, if I open that vessel up and start mixing it with air, which corresponds to this point, I go through the flammable zone, and that creates the potential for a fire. This is what we want to avoid. So the strategy that we'll employ, we're going to try to find the fuel concentration where if I did mix it with air, I still avoid the flammable mixture. So I can do that, for example, by shifting down, and I'm going to move this point to still be on air. I still haven't gotten to it quite yet. I need to tweak my line just a little bit more. And this is getting close, still just a little bit more maybe. There. So from here, I can conclude that if my fuel composition, reading the fuel composition off of this axis, is 15% or less, even if I mix that fuel nitrogen mixture with air, I still avoid the flammable region. And that is what I want to do. So just generally, the way that you would find this on the graph is you would draw a line from the air point, 79% nitrogen, 21% oxygen, 0% fuel, to the tip of the nose, and then you would extend that line, and then you would read the fuel composition off the fuel line. That is what we call the out-of-service fuel concentration. And again, that number will be relevant in the next video when I talk about the inerting calculations. So this is my OSFC. And recall, of course, that different fuels have different shapes of this flammable region. So this is just an example. So it's not always 15% is the point. Another situation that you might be interested in is if you are preparing to put a vessel in service. So let's say the vessel that we just took out of service, we had it offline for a week or two, and we did the maintenance or the cleaning that we needed to, and now we need to prepare to put it back into service. So here what I'm doing is preparing for the possibility that I have air in the vessel already. I'm going to close it, seal it up, and then start reintroducing fuel into that vessel. So if I do that, again, I'm starting with air. And if I just add fuel to that vessel, I'm connecting it with 100% fuel. Again, look what happened. It's going to trace the exact airline. You see the airline goes through the flammable zone. So this is called the in-service oxygen concentration because it's the composition of oxygen that I need to reduce to in order to bring the vessel into service. The idea here is exactly the same. So I'm going to do this by drawing lines, but the point is I want to move the air line to the right, which corresponds to increasing nitrogen, decreasing oxygen, such that when I mix it with fuel, I completely avoid the nose of this graph. So here's what the construction of that line looks like. Again, the procedure is similar, just in a different way. I'm connecting the air point to the tip of the nose and then extending it and reading the oxygen composition off the graph. Now be careful here because it's very easy to make a mistake and conclude that, oh, it's 89% because it's pointing right at the 90. Remember, the bottom axis on this ternary diagram is nitrogen, not oxygen. So for oxygen, I need to be reading off of this axis. So I would conclude here that the in-service oxygen concentration, or ISOC in this example, is about 11.5%, I would say. If I can reduce the oxygen composition to that much, and then I mix it with air, I completely avoid the nose. So there are some equations that are listed in the book where you can plug in numbers to find it analytically, the ISOC and the OSFC. I personally don't like to use those. The way I prefer to do it is graphically. I think it's just as easy and you don't lose all that much precision. But just be aware if you prefer the equation way, those are available in the book. All right, that'll conclude this video.